Welcome to sitza.com here. In the second part of this VSEPR theory concept, we look what will be the shape of a molecule, how the shape of a molecule will change from the regular patterns, the things that we learned in our last video, by introduction of the lone pair. Okay, suppose we have if we have an AB3 type molecule, central atom A, and there are 3 B atoms, we know that the shape is trigonal planar. All the atoms will be in one plane. And if you have an AB2 type molecule, and then the molecule will be linear, and if it is AB4 type molecule, it will be tetrahedral. We have learned all these things in our last video. Now what if you have a lone pair? Say for example, let me do a little bit modifications to this one, right? Suppose if I have AB3 type molecule here, this is what we call as an AB3 type molecule. Okay, and this is an AB2 type molecule here, and this is AB4 type molecule, and we don't have any lone pair anywhere, right, in the three. Now what if we do some modifications here from the AB3 type molecule? Suppose if I replace this atom B here by a lone pair. So that means I'll get a molecule like this. This will be the AB2 type molecule, but it has a lone pair 1, and now bond pairs will be 2, correct? Because I want to replace this one of the atom B here by a lone pair. So the shape will be like this: atom A in the middle, then B atom is there, B atom is one more there, and you have a lone pair of electron over here. So rather than the atom B over here, we have a lone pair. Now this is a molecule. If you look at here, this molecule, AB2 type molecule with 2 bond pairs, 1 lone pair. It's not a trigonal planar shape, right? This is not a trigonal planar shape. Rather, this will be called as a bent shape, right? This will be a bent shape here. So simply by inserting a one lone pair, or you can say replacing a bond pair by a lone pair, you get a bent shape. And if you add here the bond pair plus lone pairs, that is 3, correct? So that means the basic structure from which you can guess the shape of a molecule will be a trigonal planar, right? If you find a molecule and you find its lone pair plus bond pair is 3, correct? So you can say its basic structure will be its parent structure, like that. You can say it will be trigonal planar. Then you will see how many lone pairs are there and how many bond pairs are there, and accordingly you're going to replace one by one and determine the shape. Now let me take another molecule here, the methane molecule, right? Methane, we know it's tetrahedral. All the hydrogen atoms are around it tetrahedrally. Now let me take here a certain example first. If you look at the sulfur dioxide here, sulfur, it is double bonded with the oxygen. There's a double bond oxygen also, and there's a lone pair electron on the sulfur, because sulfur has 6 electrons in the valence shell, and it shares the 2 electrons with one oxygen, 2 more with other oxygen, right? So now you got a molecule like this. Now looking at the central atom sulfur, if you count the number of lone pairs or the bond pairs, you can see here the lone pair is 1. But how many bond pairs are there? 1, 2, 3, 4? No, you can't calculate like that, because once you want to find the as per the VSEPR theory, if you have a multiple bond, right? Suppose you have a double bond between the 2 atoms. Suppose we have a double bond, it will be treated as a one electron pair. Okay, no matter whether you have a double bond or you have a triple bond. So to determine the shape, we can treat this one as a 1 electron pair, correct? 1 electron pair. That means in the sulfur dioxide, around the sulfur, you can say there are only how many bond pairs? This will be considered as a 1 electron pair, and this one as a 1 electron pair. So that means there are 2 bond pairs are 2. So if you look at the total number of electron pairs and the bond pairs and the lone pairs, that is 3. So that means the parent shape will be a trigonal planar, right? And now you have sulfur in the middle. Rather than A, you have a sulfur, and you're gonna replace one of the bond pairs here by a lone pair. So that means I'm going to put here the lone pair of electrons over here on the sulfur. And there are two oxygen atoms, so the shape will be like this. So that's why in the sulfur dioxide, right, we have a band shape. Okay, we have a band shape. But in the carbon dioxide, if you take another example of, suppose the carbon dioxide looks like same, central atom A, carbon dioxide, right? And then two oxygen atoms. But the difference here is we have a lone pair with the sulfur, but we don't have a lone pair with the carbon. So if you have a carbon atom there and it does not have a lone pair, it only has two, oxygen atoms there. And when you count the number of electron pairs around it, right, we have only two bond pairs around the carbon. We don't have any lone pair. So that means this carbon dioxide molecule, it will resemble AB2 type of molecule with lone pairs 0 and bond pairs 2. Correct? So when you add the lone pair plus bond pair, it is 2 only. So the molecule will be linear, right? Molecule will be linear. But in case of sulfur dioxide, it resembles with AB2 type molecule with lone pairs 1, bond pairs 2. Total is 3 here. So its parent molecule, you can say, is AB3 type molecule with lone pair 0, bond pair 3. So that's why carbon dioxide is linear, sulfur dioxide is band shape. We have learned also that for a tetrahedral molecule, the bond angle is 109 degrees. And let's have a quick look at the tetrahedral molecule. You can see central atom A attached with the 4 B atoms. The bond angle, every angle is 109.5 degrees. Now what if you replace one of the atom here and you put there the lone pair? What do you expect? Do you think this, there will be the change in the shape? Yes, obviously, correct? If you, suppose replace here the one atom and you put there a lone pair, so what will be the shape? For a tetrahedral molecule, we know the bond angle is 109 degrees, and here this molecule, this is an AB4 type of molecule. Lone pairs are 0, bond pairs are here actually 4. So now suppose I'm going to replace here one of the bond pairs, okay, by a lone pair. I'm going to replace here one of the bond pairs by a lone pair. So what do you get? You get an atom A there with the 3 B atoms around it, like this. So the shape will not be a tetrahedral, rather it will be a pyramidal shape, right? So the shape is pyramidal. So one such example is ammonia, NH3. Nitrogen there with the lone pair of electron, and hydrogen also. There are 3 hydrogen atoms. 3 hydrogen atoms around the nitrogen, and there is a lone pair of electron. Total number of lone pairs plus bond pairs around it is 4. So you can say the basic shape is actually the tetrahedral. But since one of the lone pairs is there, that means in ammonia we can't expect to have a tetrahedral shape. Rather it is a pyramidal shape with a lone pair of electrons on the nitrogen atom. As you can see here, nitrogen in the center, in the middle there, and it has got 3 hydrogen atoms around it, right? So it's not like a tetrahedral, rather it has a pyramidal shape. Here this is the tetrahedral shape, and here this is a pyramidal shape. If you look at here, the number of electron pairs around the nitrogen or the carbon here, both are same. Look at this one. number of electron pairs. I'm talking about the number of electron pairs. That means total number of bond pairs and lone pairs. Here bond pairs are 0, only 4 lone pairs. Here you see that in the ammonia we have 3 bond pairs and 1 lone pair. So total is 4, correct? So that means around the carbon and around the ammonia, around the nitrogen here, electron pairs are same, but since there is a difference in the electron pairs, there is a difference in the bond pairs and the lone pairs. That's why in carbon it's tetrahedral and in ammonia there is a pyramidal shape. What if you're going to replace here 2 bond pairs by the lone pairs? Okay, suppose I'll replace this one and this one. That means I actually have a tetrahedral shape like this, isn't it? So we got here the 4 B atoms around the central atom A. And what if I replace here this bond pair and this bond pair? Any 2 bond pairs you're going to replace by the lone pair. So how the shape will look like? Okay, so we can say here the shape will be like this, isn't it? So you have a lone pair of electron over here and you have a lone pair of electron over here. Now this is the molecule. It doesn't resemble with the tetrahedral shape, correct? It is what we call as a band shape, right? It's also the band shape here. Here the central atom is having 2 lone pairs and 2 bond pairs, right? So that means this is a molecule like AB2 type molecule with lone pairs 2 here and bond pairs are also 2. So total number of lone pair plus bond pairs is 4. So you can say the basic structure or the parent structure from from which you can draw the structure of this AB2 type molecule will be tetrahedral, correct? And since we know that lone pair repulsion is more, always they will repel each other. So because of more repulsion here, they will push these B atoms slightly closer. Okay, that's why in case of a band shaped molecule, the angle is not what you find here in the tetrahedral. It will be less than 109.5 degrees. Let's take here an example of the water, H2O. Okay, water. We have an oxygen there in the center. There are 2 hydrogen atoms around it. So that means there are 2 bond pairs. But oxygen, as we know that it has 2 lone pair of electrons also. So that's why you can see the shape here in the water is band shape. And the total number of electron pairs around the water is 4. Here you see the lone pairs 2. The bond pairs are also 2. So total number of lone pair plus bond pairs is 4. So because of the more repulsion here between the lone pairs and the lone pair bond pair here, the 2 hydrogen atoms will be slightly closer and the angle will not be 109.5 degrees. Rather here in the water it will be less than 109.5, and in the water we have found it is around 104 degrees, right? Here is our water molecule. This is the oxygen here right in the center, and these are the 2 hydrogen atoms, and this is our parent methane, right? Hope you got the concept. Thanks for watching the video. Bye for now.